Let's talk about how the correlation coefficient rho affects the shape and orientation of the bivariate normal distribution while keeping the other variables constant. And we plot both 3D probability density function and their corresponding control plots. And we assume the mean mu's are both zeros and the standard deviation sigmas are both 1. First, when rho is equal to 0, that means there's no correlations. The probability density functions appears as a symmetric bell-shaped surface, which is centered at the origin, which indicating that their two variables are independent and have equal variance, and the contours are circular, which reflecting that there's no linear relationship between these two variables, so changes in one variable don't predict changes in the others. And second, when rho is equal to 0.8, which suggests a strong positive correlation, the peak is elongated along the line y is equals to x, which showing that they have high values of one variable are associated with high values of the others, and the ellipses are stretched along y is equals to x, which indicates a strong positive linear relationship. As one variable increases, the other is likely increase in proportionate manner. And third, when rho is equal to negative 0.8, which suggests a strong negative correlation. So this distribution is also elongated, but along with the line y is equals negative x. These ellipses are oriented along with y is equals negative x, which indicating that there is a strong negative relationship as one variable increases, the other decreases. Let's try to explore how changing the standard deviation sigma 2, which is our second variable in this bivariate normal distribution, affects its probability density function and this corresponding control plot while keeping the other parameters constant. So we just assume mu1 is equals mu2 equals 0. So both variables are centered at 0. And sigma 1 is equals 1, which means this is the standard deviation of the first variable, it is fixed, and rho is equal to 0.5, which means it is a moderate positive correlation. When sigma 2 is equal to 0.5, this distribution is elongated along the y-axis because sigma 2 is less than sigma 1, so the peak of this probability density function is higher since the spread is more concentrated around the mean. The contours are stretched vertically, which indicating we have higher variability along the x-axis relative to the y-axis. When sigma 2 is equals to 1, this distribution appears more symmetric because sigma 2 equals sigma 1 equals 1, so these contours roughly circular, which reflecting similar variability in both variables, so the peak of this probability density function is lower compared to when sigma 2 is 0.5. When sigma 2 is equals to 2, this distribution is elongated along the x-axis because sigma 2 is greater than sigma 1 now, so the probability density function spreads more widely, which indicating a greater dispersion of values along the y-axis. So the contours are stretched horizontally, which showing higher variability along the y-axis. So increasing sigma 2 spreads this distribution along the y-axis, which lowers the peak of this probability density function and changes the shape of this contour from vertical elongation through the circular to the horizontal elongation. So this demonstrates how the sigma 2 influences the spread and orientation of this distribution in relation to with the fixed sigma 1 and correlation coefficient rho. Let's talk about how changing the standard deviation sigma 1 of one variable influences the probability density function of a bivariate normal distribution while keeping the other standard deviation sigma 2 and the correlation coefficient rho constant. In the first scenario, sigma 1 is equals to 1, so this distribution is tightly concentrated around the mean 0, 0, which indicating they have low variability in the first variable. So these contours are closely packed and circular, which suggesting they have little to no correlation influence and equal variance along both axes. In second scenario, when sigma 1 is equals to 2, the spread of this distribution increases compared with sigma 1 is equal to 1. So this indicating that we have higher variability. The contours begin to spread out further, which reflecting the increased variance in the first variables. However, they still remain relatively circular due to the constant sigma 2 and rho. In the third scenario, when sigma 1 is equal to 3, this distribution becomes even more spread out, with a notable decrease in peak height, which corresponds to the dilution of the probability density as the variance increases. So the contours are more widely spaced, which clearly indicating that high variability in the first variables. So they still maintain a somewhat circular shape, which emphasizing that the rho is constant and there's no influence in the shape dramatically. When we increase in sigma 1 while keeping sigma 2 and rho constant, which will result in a broader spread in this distribution along with the x-axis, which is our first variable, and it will decrease in the peak density but covering more area, which is indicative of a higher uncertainty or variability in the first variable. So the contour plot provides a top-down view of this spread, which illustrating the increasing radius of this probability density as sigma 1 increases. So this visual and quantitative change in this plot clearly show how sigma 1 affects the shape and the spread of this distribution. Let's demonstrate how the bivariate normal distribution changes with different values of the mean mu1 and mu2. Well, we will keeping the other parameters constant. For simplicity, we just assume the standard deviation sigma 1 equals sigma 2 equals 1, and the correlation coefficient rho equals 0.5. In the first scenario, mu1 and mu2 is equal 0, 0, which is the default scenario where the both means are centered at 0. So the peak of this distribution is at the origin, which indicating that we have the highest probability density at 0, 0. In the second scenario, mu1 and mu2 equals 2 and 0. Just by setting mu1 to 2 and keeping mu2 at 0, this peak shifts along the x-axis to 2. So this shows how this variable corresponding to x now has a higher mean, which is shifting the center of this distribution to the right. In the third scenario, when mu1 and mu2 is equal 0 and 2, so mu2 is set to 2, which is shifting the peak along the y-axis. This demonstrates that y variable has a higher means, which is moving the center of distribution upwards to 2. And in the fourth scenario, mu1 and mu2 is equals -2 and -2, so both means are negatively shifted, which is moving the peak to -2 and -2. So this shows a combined effect, where both variables are expected to have lower values. So just by examining these plots, we can see that altering mu1 and mu2 effectively translates the entire distribution in the direction specified by the changes in the means, without altering the shape of this distribution, as the covariance structure remains constant. This helps us to understand how the location of the highest probability density area of this bivariate normal distribution is influenced by its means.